Welcome to The Explainer. Today we're answering a question we literally see the results of every single time we scroll through our feeds. How exactly do machines create stunning visual art from just a few simple words? We see these surreal, mind-bending images all the time, but the underlying mechanics are, honestly, even more fascinating than the art itself. So let's just dive right into it. Think about it. How does a machine without eyes or hands turn a simple prompt into a masterpiece? Or in our case, how does a computer draw an elephant? It doesn't hold a paintbrush, and it certainly doesn't have a visual memory like we do. As you'll see, it all comes down to math, massive amounts of data, and some incredibly clever architecture. To figure that out, we're going to step inside the AI Artist Studio. We'll look at the magic of AI art, peek inside the neural network, explore GANs in the adversarial game, check out diffusion models, which is basically sculpting from noise, talk about VAs and hardware, and finally, look at the real-world impact and risks. All right, Section 1, the magic of AI art, peeling the onion. We see tools like DALL-E and Midjourney doing what looks like actual magic. But beneath it all, it's just a machine recognizing patterns. The foundational brain of our AI artist is an artificial neural network. It's vaguely inspired by biological brains, but here's the kicker. There's no human coder sitting there programming task-specific rules or step-by-step drawing instructions. Instead, you just show it millions of examples, and it figures out the underlying rules entirely on its own. Moving on to Section 2, inside the neural network, the brain. So how does this artificial brain actually process the visual world? Well, to a computer, a picture isn't a picture at all. It's literally just a grid of numbers. Imagine a tiny 7x7 pixel image of a smiley face. That gives us 49 pieces of raw numerical data that enter the input layer. From there, they rapidly travel through the hidden layers, which analyze and transform that data. Earlier layers might just detect simple edges or colors, while deeper layers combine those edges to understand complex shapes, until the output layer finally produces the result. And all of this learning, it happens through a process called backpropagation. Basically, it's an endless try, measure, adjust loop. First, the forward pass, where the network makes a prediction. Then, a loss function brutally calculates exactly how wrong that prediction was from the truth. Next, in the backward pass, that error is propagated back through the network, and the connection weights are slightly adjusted to reduce the error. Millions of iterations later, it actually gets it right. Which brings us to Section 3. GANs, the adversarial game, or the forger and the detective. Now that our basic brain can learn, let's meet our first specific type of AI artist, generative adversarial networks, or GANs. These operate on a brilliant cat-and-mouse game. You've got the generator acting as a forger, transforming random noise into synthetic data to mimic real training images. Then, you have the discriminator acting as a detective, deciding if the image is real or a fake from the generator. They train each other in a relentless adversarial loop to trick the system until the fakes are flawless. And because this architecture is so effective, it spawned a whole family of specialized GANs. Vanilla GANs are your basic setup, but say you need control generation using specific labels. Conditional GANs, or CGANs, handle that. Deep convolutional GANs use CNNs for high-quality structured data. And if you want ultra-high-resolution images with fine-grained control, or to translate image styles like turning a normal photo into a painting, StyleGAN and CycleGAN give creators that exact kind of granular power. All right, Section 4, Diffusion, sculpting from noise, a different kind of artist. While GANs are incredibly powerful, there is another major technique taking over modern image generation. Instead of a forger and a detective, think of a diffusion model as a sculptor methodically chipping away at a block of static noise. These models create images by starting with completely random static noise and gradually removing it, step by tiny step, until a beautifully clear, highly detailed masterpiece forms. So how do these two heavyweights actually stack up? Well, GANs are lightning fast, perfect if you need real-time outputs, and they produce very sharp images. But they can suffer from training instability and something called mode collapse, where they lazily generate the same few images over and over, lacking variety. Diffusion models, on the other hand, take a bit longer to generate results by reversing that noise, but they are highly reliable and produce incredibly detailed images. It's a classic trade-off. Moving to Section 5, VAEs and hardware power, the engine room. Before we get into the real-world stuff, we have to look at one final model type. Variational autoencoders, or VAEs. These work by compressing complex input data down to a simpler version with fewer details, finding the absolute essence of an image, and then rebuilding it.
This gives developers incredible power to create controlled variations. You can spot unusual patterns or generate similar but different outputs really easily.
And look, all of these billions of calculations require immense computing muscle. We are talking serious hardware here. The heavy lifting is done by GPUs, general-purpose chips built for parallel processing that are linked together to handle computationally intensive AI training. Add in FPGAs, which are hyper-specialized chips that can literally be reprogrammed on the fly to efficiently tackle image and video tasks, and you have an incredibly powerful engine room driving all these AI artists. Finally, Section 6, Real-World Impact and Risks, Beyond the Studio. Now that we really understand the mechanics, let's look at how this technology is fundamentally changing our world. And it is massively scaling human effort across the board. In enterprise, it's automating content generation. In creative industries, game creators are prototyping environments and storyboarding in minutes. In regulated domains, it's summarizing clinical notes or legal reviews. And in scientific research, it's doing mind-blowing stuff like simulating complex medical MRIs or helping discover new molecular structures. But of course, there is a catch. As Palo Alto Networks points out, generative models often produce content that's fluent but false. These are known as hallucinations. Because these systems are built to predict patterns rather than verify cold hard facts, they sometimes generate totally plausible-sounding outputs that simply aren't grounded in any real data. They sound confident, but they're entirely fabricated. So alongside this absolute technological magic, society is navigating some very real ethical implications and risks. I mean, malicious use is a big one, generating misinformation, deepfakes, and impersonation. There's the risk of amplifying cultural bias because the AI learns from training data that inherently contains human annotator bias. We're dealing with massive copyright and ownership debates regarding proprietary data, plus the sheer financial and energy resource costs required to run these models limit equitable access for everyone. It's a lot to untangle. So as we leave the AI Artist Studio today, I'll leave you with this question to chew on. We now understand the math, the adversarial games, and the noise sculpting behind the magic. But in a world where machines can generate photorealistic images in seconds, what exactly is the future of human creativity? How will our own definition of art and human expression evolve? Thanks for joining me for this explainer, and keep questioning the magic behind the machine.